So I think we can start now. Can you hear me? Okay, so let me share my screen. Can you see the screen? Okay, so just some announcement. So the assignment 2 is due on tomorrow midnight, and the solution will be uploaded on the next day for your revision. And the midterm will be on next Monday during the lecture time. And you will cover chapter 1 to chapter 5. That's from the history to the chapter of symmetry. So this is just some announcement. So we can start discussing the questions today. So the exercise question today is still focused on the chapter of symmetry. And for the first question, we are given an alpha particles, and we want to conclude about the isospin of the alpha particles. So to determine the isospin, we can just refer to this diagram. So we know that in the horizontal rows, like neutrons and protons, they have similar mass but different charges. So we can assign an isospin I to each row. For example, for neutron and proton, we assign an isospin of 1/2 to them, and they form an isospin doublet. So, but here for alpha particles, we are given that we cannot find other particles with similar masses. So the alpha particle is 2 protons and 2 neutrons. So the possible candidates to form an isospin multiplet is a helium-4 nucleus, is a hydrogen-4 nucleus, or lithium-4 nucleus, but they all do not exist. So the alpha particles just exist in their own. And so we can conclude that the alpha particle is possibly an isospin singlet. That means the I is equal to 0, and the isospin state of an alpha particle is 0, 0. So that's the argument for the first part. And for the B part, we are given a process, D plus D to alpha plus pi 0. And it's given that this process has never been observed. And we want to explain why is the case. And usually, if a process cannot be observed, then you must violate some conservation law. So here we can consider the isospin. So for the left-hand side, the deuteron have an isospin I equals 0. So in lecture, you possibly know that deuteron is something like Pn minus Np. So it's an isospin singlet. So the isospin stays just 0, 0. And we have 2 deuteron. So we just add 2 0, 0. And the result is also 0, 0. And on the right-hand side, we have an alpha particles, which is 0, 0, according to A part. And for the pions, you can once again refer to the diagram. So we can see that we have 3 pions on the same row, and they have similar masses. So they have the isospin of 1, and the pions is in the middle. So the I3 is 0. So the isospin state of pions is 1, 0. And so adding them up, the total isospin state will be 1, 0. And here we can see that the I will change from 0 to 1. And so this process does not conserve isospin. And that's why we haven't observed this process. So that's the explanation to part B. And for part C, we are asked whether we expect beryllium 4 to exist, and also for 4 neutrons. And beryllium 4 just refer to the states of 4 protons. And here we have 4 neutrons. And so we can see that there are some bound states of 4 nucleons. And before discussing the case of 4 neutrons, we can first look back to the case of 2 nucleons. So for 2 nucleon states, we have 4 possibilities: PP, NP, P, and NN. But these states are not all eigenstates of the total isospin. So for convenience, we can first do some combinations so that they become the total, the eigenstate of the total isospin. So here is the result. We have an isospin triplet and an isospin singlet. And the meaning of a triplet is that we can transform each state by rotation in an isospin state so that it can transform to other states. That means for PP, we can do some rotations and it will rotate to this state. And also we can rotate this state and we will rotate to this NN state. So that's meaning of triplets. And for the singlets, no matter how we rotate the states, it will always get back itself. So that's why we call it singlet. And an important note is that if one of the states in a multiplet does not exist, then it automatically implies other states also do not exist, because they are just related by rotation. So if one state does not exist, then all the states in this triplet should not exist also. That's the key point for our discussion for 4 neutron state. And here we have some special notations. We say that 2 times 2 is equal to 1 plus 3. That means 2 means that the isospin doublets. So when we have a composite system of 2 nucleons, we can decompose it into an isospin singlet plus an isospin triplet. So that's how people usually denote this. So now we can discuss the case of 4 nucleons. So in the case of 4 nucleons, in total we have 16 states. So we have PP, and we have four possible states in which one of the protons is replaced by the neutrons, and we have 6 states in which 2 of them are replaced by neutrons, and we have 4 states in which 3 of them are replaced by neutrons, and we also have 1 state which is all neutrons. So in total we have 16 states. But just like the case of 2 nucleons, they are not the eigenstate of the total isospin. So we can recombine them and form some isospin multiplets. So first we can form an I equals 2 multiplet, and it will contain 5 states, and 2 of them will be the PP and NNN, and in the middle we can also have some superposition of this. So it's just like in 2 nucleons case, we have PP and N and some PN plus NP. So it's just like the 2 nucleons case. And for the superposition of the PPPN, we know that it refers to lithium-4, right? Because lithium have 3 protons in it, so this will refer to lithium-4. And similarly, for this state, it will refer to hydrogen-4. But we are given that in part A, we are given that they are not exist. And so according to our previous discussion, we can know that all the states in this multiplet cannot exist. And so the beryllium-4, which is the state of PPPP, and also the state of NNNN should also not exist. But apart from I equals 2, we can also have an I equals 1 triplet. But the argument is the same because it must involve the states, which is some superposition of this or this. But we know that they does not exist. So all these states in the triplet should also not exist. And finally, we can have an I equals 0 singlet, which is some superposition of PP and N. And we know that this is corresponding to the alpha particles, and it can exist. So the conclusion is that the beryllium-4, which is 4 protons, and also the state of 4 neutrons should not exist. And the only possible one is the singlet state, which will correspond to the alpha particles. And in this case, we can write in this form. So we have 4 nucleons each nucleon is an isospin doublet, and it can be decomposed into the 5. 5 means the I equals 2 multiplets, and we have 3 triplets and 2 singlets. So that's the case for 4 nucleon states. So basically, it's just similar to the case of 2 nucleons, but it's just more complicated. So let's discuss the second question. So the second question is asking about parity. So for A part, it asks whether neutrino is an eigenstate of the parity operator. And neutrino is a very special kind of particle in the standard model. And the main reason is that in nature, we only observe left-handed neutrinos. And one action of the parity operator is that when it acts to states of left-handed, it will turn the left-handed state to a right-handed state. So if we act the parity operator on a left-handed neutrino state, it will turn it into a non-existing right-handed neutrinos. So obviously, the neutrino is not an eigenstate of the parity operator. So a neutrino do not have a intrinsic parity, unlike other particles. And for the B part, we want to know which of the process violate parity conservation. So to do this, we can refer to the lecture slides on calculating the intrinsic parity of the particles. So on the left-hand side, we have the kaons. And kaons is one of the pseudo-scalar meson. So if the parity will be -1. So on the left-hand side, the P is equal to -1. And on the right-hand side, for the case of 2 pions, you just have to multiply 2 minus 1, because for a pions, the parity is -1. So for 2 pions, it's just -1 square. So the parity on right hand side will be +1. And for the case of 3 pions, it's just -1 cube. So the parity is -1. So here we can see that for the 2 pion case, it does not conserve parity because P will turn from -1 to +1. Okay. And for the third question, so this question is some discussion on the interconversion between two hadrons. So in lecture, we have learned that K0 and K0 bar can interconvert each other by these two diagrams, and we want to find whether there are other hadrons which can interconvert each other. So in this question, we are given three conditions. So first, A and B should have the same mass, and this implies that they are antiparticles of each other. And the second requirement is that they have the same charge, and they also should have the same baryon number. And combining 1 and 2, we can see that A and B should be neutral, right? Because if A and B, so let's say A have a charge of +1, and then according to condition 1, the B is an antiparticle of A, then B will have a charge of -1. And this will not satisfy the second requirement. And so A and B should also should be neutral. And similarly, if we combine condition 1 and 3, then A and B should be mesons. So let's say if A is a baryon, then you will have a non-zero baryon number. And since B is an antiparticle, so it will be it will have a different baryon number with A. So A and B should can only be mesons, which have 0 baryon number. And so combining, we have shown that A and B can only be neutral mesons. And the next step is to identify the possible quark contents. So we know that they are neutral mesons. And just to remind you that a meson is composed of a quark and antiquark. And since we require it to be neutral, so Q1 and Q2 should be in the same row. That means in order for the meson to be neutral, Q1 and Q2 should be in the same row. So one possibility is that we have UU bar and DD bar, CC bar, etc. But in this case, the antiparticles will be the same particles. That means that particle A and B will be the same particles. So it's not interesting to discuss this case. And so discussing this case, we have only 4 cases remain. And note that the top quark, because it's unstable, so it cannot form a bound state. So we only left with 4 cases: the UC, DS, DB, and SV. And from the quark contents, we can conclude that the candidate mesons are the D mesons, kaons, B mesons, and the strange B mesons. So these are the 4 possible candidate mesons which can undergo interconversion. Okay, and student asks why we don't consider top quark here, because if we refer to the standard model, the top quark has a very high mass. It's about I don't remember. It's maybe 107 GeV or so. So it's a very unstable particles, and it will, and before it can form any bound states, it will quickly decay into some other thing, so it will not form a stable bound state. About US and UB. So as I said, if the meson should be neutral, if we form US bar, then it will be a charge of +1. So it will not be neutral. And similarly for UB bar, it also have a charge of +1. But because a quark have a charge of 2/3, and the anti-quark have a charge of -1/3. So when we so if we add the charge of U and S bar, they will have a charge of +1. Okay, so let's go to the last question. So last question is somehow related to question 3. So it asks why we can't mix a neutron and anti-neutron in the way that we do for kaons and kaon bar. And let's suppose we can mix neutron and anti-neutron. Then that means it will imply the conversion between a neutron and anti-neutron. But this conversion will violate baryon number, because neutron have a baryon number of 1 and anti-neutron has a baryon number of -1. So the interconversion will violate the baryon number conservation. So this so that's why we do not see a mixing between baryons. And that's also why you have the condition here. And next, it asks why don't we see the mixing between kaon star and kaon star bar. And according to a hint, we know that these two particles are some sort of excited states. So if you remember, for hydrogen atom, This is just a bound state of proton and electron, and we solve the energy states. We have some L0 states, some L equals 1 states. And the ground state also is always the L equals 0 states. And similarly, we can also solve the energy state of 2 quarks. But although the solution is much more complicated, but in general, it's very similar to the case of hydrogen atom. We still have some L equals 0 states, some L equals 1 states. And here the K star bar, the K star is L equals 1 state. So it's in excited states. So it's not a stable particles. And so these two states will quickly decay before they can the interconversion can happen, and that's why we don't see the mixing between them. And so that's the reasons. K-meson cell is also not stable. Yes, it will also decay into pions, but the case here is that it is unstable, that it will decay even before any conversion can happen. And for K-meson, the decay time is relatively long, so we can observe the mixing between K and K bar. So basically that's the end of the exercise question. And if you have any questions about the homework 2 or the midterm, you can ask now, or you can send an email to me.
May I ask a few things about this exercise? So basically, so decay governed by the weak interaction, and it has this typical length scale of, I think, 10 to the minus 13 seconds or something like that. But how about this exciting state to ground state? Like what mechanism govern this this change of states, essentially? What governs this mechanism? Because when we talk about timescale, we talk about the timescale of a certain mechanism. And so what is the thing that's behind this excited state to ground state mechanism?
Okay, so let me check that. So the K star basically you decay into K plus and pi minus, and K star bar will decay to K minus pi plus. And about the mechanism,
Wait, so you're saying that the K star and the K star bar, they decays also fire the weak interactions. Then why does the excited states would decay much faster than the relatively stable K naught? So essentially, what makes excited state decay faster?
let me see. It does not have an explanation here, but yeah, but as you know, weak interaction do not have a specific time scale like strong interactions. You have a very large range.
Mm-hmm.
So for an excited state,
because the other thing I would think about is the excited state has a larger energy content. So
yeah, it also depends on the mass difference between your final states and your initial states. That will also be an effect here. So it's hard to say why is faster, why is slower.
but the entire argument here in the slide is because they're excited states, therefore they will decay faster. But it doesn't, you know, because K on will also decays, and then K star is also decays, but you're saying that K star is excited states, that's why they decay faster. But as you just mentioned, there is no...
Yeah, the key argument here is just they decay faster than the rate, than the conversion rate.
Right, but K on also decays.
And that means they decay slower because before the conversion.
Yes, but why does the K on decay slower?
Yeah, I see your point, but
I wouldn't know that before you...
Yeah, so we are just, what we are doing here is just try to explain what we see.
Okay. So if you go back to several slides before, you talk about the the direct product of two times direct product of two, you can decompose it into direct sum of 5, direct sum of to the direct sum of 3, and that kind of thing. Yeah, the next one. How do I know about this decomposition here?
So in principle,
no, I mean the 2 times 2 times 2 equals to 5 plus 3 plus 3 plus 3 plus 1 plus 1. This one.
Do you know how to decompose two neutron state?
Well, technically no.
So basically it's some diagonalization process. So because we want to, so as I say, they are not the eigenstate of the total isospeed. So we can, let me see like this.
Right.
Let's
If you
consider
talk
the
about
spin.
the diagonalization, that would be fine, but because here we're talking about direct product and direct sum, so I thought there was some arithmetic in between that I can, directly jumping from direct product to direct sum instead of going through the diagonalization.
Oh, wait, what do you say?
So
Yeah.
your direct product and direct sum are two arithmetic symbols here. So I thought there would be some arithmetic procedures where I can directly jumping from the direct product of something to the direct
no, you
sum.
have to go through the diagonalization procedure before you can write down this.
Okay. Okay. So there's no direct way jumping from the left to right or vice versa. Okay. Finally, also staying around these slides is what does it mean when you're physically jumping from a triplet state to a singlet state, like physically, what is going? So if you look at something, look at a particle, now you tell me it is a singlet state, and then what do you have to do for it to jump to a triplet state?
You cannot jump through this. So if it is a singlet state, you will always be in a singlet state because that's a symmetry. Just like if you are in I equals 2, then no matter how you transform, you will always in I equals 2 state.
But okay, then how about this? If you stay in the triplet state, then you say there are three different states within it. Then how do you jump from one state from the other? I know it is in the isospin space, you talk about rotation in the isospin space, but how do you do it in physically? Like if I am in one state, one of the triplet states, how do I, like, what do I have to do for it to jump to a different state?
You mean in a same multiplet?
Yeah, a triplet or a quintet, whatever. So for instance, here you talk about,
it's just, they are just related by rotation in isospin space.
Right, but how do I do it physically? So if I observe a particle right now in the 1,1 state, what do I have to do for it to jump to the, let's say, 1 - 1 state? Like physically.
Physically, you just apply some some external let me see how to say that, right? Just like so you just imagine these are not isospin but just spin. So this will just mean two spin up particles. This will just two spin down particles. So you are just basically asking how we turn two spin up particles to two spin down particles.
Mm-hmm.
Then we just apply some external magnetic fields. So back to this case of two neutron states. I'm not very sure about how physically we can do that, but just do an analog, so we can do some external field so that we can change the isospin state. I'm not very sure. Yeah.
Yeah, because spin is I mean, is kind of responsive to the magnetic field. But iso spin, I don't know what field does it correspond to.
I also not sure. Maybe I have to check.
All right. Just finally, when we talk about we can only find left-handed neutrinos, how do we actually measure its parity? Like you have a neutrino there, but how do you measure this parity?
In high, well, so in relativistic limit, the hand, that means handedness or chirality will just similar to the helixity. Have Professor mentioned this?
I'm not sure.
So just in high speed limit, chirality is just helixity, and helixity is just the spin direction projected on the momentum. So we can simply measure the spin and also the momentum of particles to determine the helixity and so determine the chirality.
I see. Okay.
Oh, there's a question in the chat box on how to internet first. How do I find the energy deposit? Or you're asking homework question? So for question 5, you just have to use the the curve in the slides to determine the energy loss. So what do you mean by deposit in copper on the internet? Oh, I see. Yeah, you just have to use the curve in the lecture slides to find the dEdx. Yeah. Okay. Any other questions? So if no, then good luck for your midterm exam. And see you next week.